Okay. So today, okay, click and close, all the way closed. Okay, so today we got a lot to cover. So we got tests coming up. We have lots of material still to take care of. So I'm going to try to be very efficient with this. I think I should be able to give you a decent amount of work time tomorrow. I think we can get through most of this today, but probably not quite all of it. So we're going to talk about applications of linear systems. This will show up on the technology test, not the non-technology test. You'll have access to Desmos matrix, Desmos graphing, and your job is going to be to set up a linear system that represents the problem that we're trying to solve. Once you get it set up, you can use technology to solve it, but you got to be able to set it up, set up the linear system. That's the part that we got to practice a little bit. And then once you solve it using technology, it's pretty straightforward to just figure out, okay, what does that mean in terms of the question that we were asked to solve? So every problem is different. There is no one-size-fits-all approach to this, but there is a strategy that I want you to use. And on the graphing test, so there's going to be two tests, right? Two very short tests. The technology test, that one, there aren't very many problems. It's possible that you could not get correct answers but still get most of the credit if you do all of these things. If you don't do these things and you don't get the problem exactly right, you're out of luck, because this is what you have to do to get partial credit. And I would assume, going in, just make the assumption that you might make some little trivial mistake and get something slightly wrong. That's not that big a deal if I see this stuff, but I got to see this stuff. So these are the steps I want to see every time you do one of these problems. Step one, you have to define your variables. You have to write down whatever my variables are. In this case, we're going to have three variables, so x, y, and z, and you need to write down what each one of those means exactly. Okay? Take time to do that. Once we define our variables, then we're going to set up equations so we can solve for those variables, and then we'll solve the system using technology. Okay, so let's read through this one, see if we can make sense of this, and we'll kind of work through a few examples and you'll get a little practice. So it says the sum of three numbers is 70. One number is 5 more than a second number. It is also twice the third number. Find the numbers. So what are the things we're trying to find here? Okay, but what's the question asking us to find? The question doesn't say anything about variables. It just wants answers. What are we trying to find? Numbers. How many numbers are we trying to find? Three. So how many variables do we need? Three. Because the variables are the things we're trying to find. So what would x be then? The first number, right? That's x, first number. What's y? Second number. What's z? Third number. There you go. We got them. So we're going to write that down. Those are what the variables mean. We defined the variables. Now we've got to see if we can come up with how many equations. Show me on your fingers. Yeah, we need 3 equations. I have 3 variables, so I have to have 3 equations. Okay, a couple things to think about when we're coming up with the equations. We always we have to have the same kind of quantity, the same, the same units on the left and the right side of the equation. In this case, there really aren't any units, so it's not such a big deal, but we have to be representing the same kind of stuff on the left and the right side of any equation, because after all, the left and the right sides are equal, right? Okay, so first of all, we always want to look for, is there a freebie equation here, a super easy one that is just like we have 3 variables, x, y, and z. Is there an x plus y plus z equals equation? We always want to look for that one because it's the easiest one. Is there an x plus y plus z equals equation somewhere? $70, right? It tells us the sum of the 3 numbers is 70. So therefore, x plus y plus z, those are my 3 numbers, must add up to 70. First equation's done, piece of cake. Okay, what's the next equation going to involve? Okay, next sentence, right? The next sentence says one number. Well, what does that represent? What's one number? So what could I want to try to make this a math sentence, an equation instead. X. Okay, good. So X is, what's that mean? Mathematically is corresponds to equals, yeah. And then 5 more than a second number. What's the second number? Y. So how do I say 5 more than Y? 5 plus Y or Y plus 5, doesn't matter, either way, right? 5 more than Y, I'm going to write it as Y plus 5, either way though, okay? There's my second equation right there. X equals Y plus 5. Okay, we need one more. How about the next sentence? It is also twice the third. Okay, well, what does it mean? One number is 5 more than a second. It is, so what's it? X, because that's what we were talking about in the last sentence, right? Is equals twice the third. What's the third number?
Z.
So how do I say twice Z?
2Z.
2Z, there you go. So we get X equals 2Z. So there's my system. Now, what kind of technology am I going to have to use to solve a system with 3 variables? Matrix. I can't graph that, right? So can I just put that in the matrix right now? Are they in standard form? No. What does standard form mean? How do I have to organize an equation for it to be standard form? X term first, then plus Y term, Z term, equals number, right? Okay, so give me thumbs on the first one. Am I good? Yeah, first one's in standard form. X plus Y plus Z equals number. We're good. Second equation, though, what do I have to do to the second one to put it into standard form? Okay, good. I've got to subtract that Y over to the other side, don't I? Right? Okay, so what's that going to give me then? The first one is already good. First one we can just leave the way it was. X plus Y plus Z equals 70. Second one, if I subtract that Y to the left side, what do I get? X minus Y, right? Because I'm subtracting the Y to the left side, minus Y equals, okay, give me a fist of 5 on that. How are we doing? Is that good? Okay. What's the only thing I have to do to the third equation? Yeah, I got to subtract the 2Z over to the left side, don't I? Right? So then I just end up with what? X minus 2Z equals, what's left on the right side if I subtract the 2Z to the left side? 0. Good? Give me thumbs on that. How are we doing? Is that good? Okay. So there's my system. All I've got to do is solve that now using Desmos matrix. How do I what?
How do you put the calculator from like normal into matrix? Or it's like a whole separate, so it's like.
It's a separate, yeah, right. You have to go to the Desmos site and then choose. There's like 6 different calculators. We choose Desmos matrix calculator. There you go. So now, what buttons do I push? New matrix. Add a row. Add 2 columns. Good. So 3 rows, 4 columns. Perfect. And I'll hit Tab to advance through the matrix. Now, what numbers do I have to input? 70. Tab. Next row.
1, negative 1, 0.
Okay, why 0?
Because there's no Z.
Ah, no Z term. Okay, good. And then
5.
5. All right. Next one.
1,
0, because there's no Y. Perfect.
2, 0.
0. There we go. Now what?
Then confirm it.
I have to hit Enter, right? So it stores it.
Then
RREF. Good.
then capital A.
And there's my answer.
You did
What do you know? Okay. All right, thanks. Okay. Okay, so, oops, what happened there? I
I
got,
accidentally did it twice.
yeah, I didn't want to do that. What's that?
Maybe you have to.
Yeah. I think this mouse is not working so well. There we go, okay. Okay, so interpret that. What's that telling me? What's this that's giving me the solution? So what's that mean? What's the first row mean? Okay, x equals, and that's the first number, right? Is 30. Y equals the second number, which is 25. Z equals the third number, which is 15. Okay, make sense? Give me thumbs. All good? All right. Let's try another one. So now that's one type you could see. Here's another type. So this is a mixture type. You see these all the time. This is something we do a lot of times with linear systems. So you'll do stuff like this in chemistry. Okay. Soybean meal is 14% protein. Cornmeal is 7% protein. How many pounds of each should be mixed together in order to make a 280-pound mixture that is 13% protein? So what does it mean if we say that soy meal is 14% protein? Like if I had 100 pounds of soy meal, how much protein would I have? 14 pounds, right? Okay. Okay, good. So first of all, what are my variables? What are the things I'm trying to find? Yeah, but what are they? What's x and what's y? What would it be? Okay, but you got to be specific. I need some units there. What am I? Pounds, right? So x is pounds of soybean meal, okay, right? Because we want to know how many pounds of each, soybean meal and cornmeal. So x is pounds of soy meal. What's y? Pounds of cornmeal. There you go, okay? Does that make sense? And you got to get those units in there so you know what you're talking about, because otherwise if you just said soy meal, that's not specific enough, right? We have to know that it's actually the number of pounds is what we're looking for x and y. So how many equations do we need? Two, because I have two variables. Is there a gimme? Is there an x plus y equals? And you see why it's so useful to have the units on there. So pounds of soy meal plus pounds of cornmeal is what? What's x plus y equal here? Does it tell me how many pounds I need? 280. There you go, right? So we're talking about pounds plus pounds equals 280 pounds. The units on the left have to equal the units on the right. Okay? Give me thumbs on that. Does that make sense? Okay, so there's my easy one. What about my tough one now? What else do we have to specify here about our mixture? We're trying to get 280-pound mixture that is 13% protein. So how much protein, actual protein, are we trying to get, or how could we find that? How much total protein should we have in our mixture? Say it again. 13% of 280, right? Does that make sense? 13% by itself doesn't tell me anything, because is it 13% of 1 ounce or is it 13% of 1 ton? There's a big difference, right? I need to know 13% of what? So 13% of 280. Now let's pause for a second and think about that. How would I say that? 13% of 280. How do we do that mathematically? If I want to take a percentage of something, how do we deal with that? Okay, Chromebooks should all be closed. What do we do? Divide? Is that what we do? We do a, like,
You have to multiply 280 by 0.
okay, good. So when we take a percentage of, we're multiplying, but we're always going to multiply. When we want to do something with a percentage, what do we have to, in math, what do we have to do to the percentage first? We got to make it a decimal, don't we? Right? In order to actually do a calculation with a percentage, we need to turn it into a decimal. So 13% of 280 is going to be 0.123, or sorry, 0.13 times 280, whatever that is. It's just going to be some number, right? Make sense? And I don't even have to figure out what it is. I can just put it into the system like that. Desmos will take care of it, right? So my second equation is going to be this 13% protein part, right? So something has to equal 0.13 times 280. And what does that represent, by the way? 13% of 280. What's the meaning of that?
That's how much protein.
Oh, okay, good. So the actual amount of pure protein that we're going to have in our mixture, right? So on the right side, we're talking about pure protein. So I better be adding up pure protein on the left side too. Okay, well, what's that going to be? What's the pure protein that's being contributed by the soy meal? Soy meal is 14% protein, and we're mixing up X pounds of soy meal. So what's that going to be? I need to figure out how much protein is being contributed by the soy meal. I'm supposed to end up with having a total of 13% of 280 pounds. What's the protein from the soy meal? 14% of how many pounds? How many pounds of soy meal are we mixing up? Do we have? No, how many pounds of soy meal?
So wait, if there's only 2, then you just cut that in half, so it becomes 14.
Well, we don't. That's what this system is going to tell us. We don't know the answer yet, do we? But we have somewhere written down what represents the pounds of soy meal. What is that? That's X, right? X is the number of pounds of soy meal, right? We don't know what X is yet, but whatever it is the number of pounds of soy meal. So then I want to take 14% of how many pounds of soy meal? X, right? 14% of X. How do I say 14% of X? I can't use a percent. What do I have to do? Okay, good. That's going to be 0.14x. That's just 14% of all the soy meal, isn't it? Right? Okay, so that's the protein from the soy meal. How much protein are we getting from the corn meal? 0.07. Why? Because that's right. I'm taking 7% of Y. That's the total weight of all the cornmeal. Everybody get that? Okay. So there's my other equation. 0.14x plus 0.07y equals whatever that number is, 0.13 times 280. Okay, make sense? Okay, that is my system, right? How would I solve that one? What are my options? I can use technology. What are my two options here? I could use a matrix, or I could, what? What's the other thing I could do? I only have two variables, x and y. So I could graph it too, right? I could just go into Desmos graphing and graph the red line and graph the blue line by just typing those into Desmos. And then how could I see where the solution is if I graph the lines? The intersection. Which one's easier? I mean, it's up to you, but personally, I think the matrix is. I think if it's already in standard form, I think it's easier just to put it into the matrix myself. Because then you don't have to go like zoom out and find the intersection, right? It just gives you the answer. Okay, so let's put this in, see what we get. Here, I'm going to move all this stuff down. Oh, I guess that won't work. I'll just leave it there. Okay, so we got to put that into the matrix. That's fine. We can do that. So there's our two equations. I need a new matrix. What size? How many rows? How many rows in my system? 2, because there's 2 equations. How many columns? 3. Okay, what's the first row? 280. Next row? Whoops, 0.14, 0.7. And then the other side, it's whatever that number is. I'm just going to write it as 0.13 times 280. That's fine. I'll just leave it like that. Times. 13% of means times. 0.13 times, right? How would you calculate 47% of 400? Yeah, 0.47 times 400 tells you what 47% of 400 is, right? Okay, percentage of means multiplying. Okay, so then I'm just going to do RREF A, and there's my answer. Okay, so you guys interpret that, please. What's that telling me? Yeah, right? This is telling me X, isn't it? Right? So that's X. So we're going to have 240 pounds of soy meal. And this is Y, so it's telling me 40 pounds of cornmeal, right? Everybody see that? Okay. So I want you to go try one of these now. Before you jump up there, let's talk about this for a second, though. Let's read through this together. How many liters of a solution of 6% hydrochloric acid and of 2% hydrochloric acid should be mixed to yield, so we're going to create 80 liters of a 5% hydrochloric acid solution. Okay, what does it mean if you have a 6% hydrochloric acid solution? Okay, but what does that mean? 6%, the solution is 6, what does 6% mean?
I don't know.
Okay.
It's diluted, so there's only like 6% of hydrochloric acid.
Okay, good. It's diluted, so only 6% of the solution is actually pure acid, right? It's diluted, so it's not quite so strong. 2% solution would be only 2% of the solution is actually acid, right? The rest of it's just water, okay? Go try this one. Go jump to the boards and try this one. Yeah. Okay, so what did we say X was? Be very careful in your answer. What is X?
6%.
Good. Okay. So it's liters of the 6% acid, right? Y is liters of 2% solution. You got to have the units in there, right? Capital L would have been better. So liters of each kind of solution. So we need to get 2 equations then. Do we have an X plus Y equals equation? So liters of strong plus liters of weak equals how many total liters? 80. There you go. Okay, now what about the other equation? So the other equation has to do with the amount, just the total amount of just the pure acid, right? So we know that we want to make 80 liters of a 5% solution. So 5% of 80, which is actually just 4, right? So we're only going to end up creating 4 liters of pure acid. It's diluted, right? It's a 5% solution, but if I just look at only the acid content, it would be 4 liters. It's that product. Okay, so on the right side, I've got pure acid. I need to have pure acid on the left side too. How much pure acid is there in X liters of 6% solution? Good, so there's 6% of X, right? That's what that says, 6% of X plus 2% of Y, right? Of the Y liters of the weak solution, only 2% of that is pure acid. So 0.02Y, there's my system. You guys threw that into a matrix and you got 60 liters of the strong and 20 liters of the weak, didn't you? Okay, good. All right. So let's see if we can crank through one more of these, maybe two more. I think we have time maybe for two more if we hustle. So here's a good example of a break-even problem. You see these a lot. Okay, these kinds of problems show up all the time. So the Rolling Fund Bike Shop estimates it will need to purchase $6,500 of new equipment to manufacture doggy sidecars for bikes. The cost of building each sidecar will be $250, and the revenue from each sidecar will be $550. How many sidecars will the shop need to sell to break even on this venture? Okay, well, first of all, what is revenue?
I think it's gonna be easy. Profit.
It's not profit. What's revenue mean?
The total money you make back.
The total money that's coming into the company, right? Yeah, so revenue is the money that's coming in. What do we call the money that's going out of a company that you're spending? Costs. Okay, and typically there are two kinds of costs. That's the money going out. The fixed costs are a one-time, usually upfront expense to buy equipment or something. You only have to do one time. And then we have sometimes incremental costs. So every time you build something, there's going to be a little bit of cost associated with building each item that you're selling, each product, right? Okay, so what does it mean to break even then?
It means you're gaining back the amount of money you're spending.
Okay, good. So the revenue catches up with the cost, right? Does that make sense? Okay, good. So let's come up with a revenue function. What's my revenue function going to be? How much money are we taking into the company? Well, first of all, they want to know how many sidecars do we have to sell to break even? What's our only independent variable going to be? What's the one thing that we can control here? The amount of cars, right? So X, our variable, X is just going to be the number of sidecars that we build and sell, right? So if we're building and selling X sidecars, how much money are we bringing into the company? Each one we sell for $550. So if I'm selling X of those, how much?
300 per car. So wouldn't it just be?
Well, no, I just want revenue. I'm not talking about profit. I just want to know revenue here. How much money is coming in? 550 per sidecar. So if I sold 10 of them, how much money would be coming into the company? Well, you just multiplied by 10, didn't you? Okay, so what if we sell X sidecars? How much money is coming in? Okay, but X times 550, right? $550 for each sidecar times X sidecars means we get 550X is the revenue. That's the amount of money that's coming in. Okay, but how much money is going out? What's our cost function? How much money are we spending for each sidecar that we build? Okay, so if I build X of them, how much money have we spent? 250X. Okay, are there any other expenses we have?
What is that before the X?
C.
Say it again.
C. Yeah, C.
The cost.
The cost, yeah, cost function. Right, so this, let me label those. So this is revenue. And this is cost. Okay, but what else, what other costs do we have? We have,
New equipment.
the new equipment. Okay, so how does that change my cost function? I add it to the amount, the 250X, don't I, right? Because that 6,500 is there whether we sell any sidecars or not. If we sell 0 sidecars, we still have spent $6,500 on equipment, right? Okay, so then if we want to find the break-even point, we're just trying to find where revenue catches up to cost. What might be a good way to use to solve this system? We could just subtract the two, right? and find when there's 0, I guess. But how can we use technology here? What technology might be useful? Yeah, why don't I graph these? Why don't I just graph the revenue line, that function, and graph the cost line, that function, and see where they intersect? Yeah, okay. So let's do that. Okay, so I'm just going to go, gosh darn it, I'm just going to go into Desmos graphing. And I just have to enter those two equations. Let's enter the revenue function. So actually I'm going to do cost first. So cost C of x equals 250x plus 6,500. Okay, revenue, R of x equals 550x. Let's make that green. Okay? All right, so then all we have to do is just figure out where they cross. Well, I can't even see them yet. So maybe I need to zoom out a whole bunch. Whole bunch. You guys tell me when you see an intersection.
Right there.
Okay, there it is right there, isn't it? Okay.
us.
There it is. Okay, so that's going to be our solution. So what's x? What's the value of x at our solution?
21.6866.
Okay, good. So there's the value of x that we were looking for. Now, you don't have to do this, but that graph is not very convenient, is it?
No.
Okay, why is that graph so bad? The graph is so bad because, look, the value that we were looking for was only like 21.6, 21.7 if I round to one decimal place. Do I need my x values to go all the way back to negative 5,000 and up to past 20,000?
No.
No. So all I'd have to do to make this graph look a lot better is go into the wrench, to the graph settings, and I'm going to go down to the x values, and I'm going to choose new ones. I don't need to go clear back to some negative thousands. I'm just going to start at x equals 0, and I'll end at x equals like, I don't know, like 40. And look what that did. When I change the x scale like that, now it makes it really obvious that that's the intersection.
Well, you're already zoomed out as far as you were.
I know, but so I'm just saying, I didn't have to do this, but doesn't that make the graph look a lot better?
Yes.
Now I can see the difference between the two functions. So the cost function is the red one, the revenue function is the green one. That's where the revenue function finally catches up with cost and we break even, right? Okay, so you guys interpret that for me, because just the numbers aren't good enough. Okay, so you tell me what my strategy is going to be then. Okay, hold on. We're not done yet. Just hang tight. I need 30 more seconds. Sit down, or you're going to be here late. We don't want to do that. So if x is 21.7, we'll round to one place. Is that the number of cars that I need to make to break even? 21.7? Anybody care to buy a 7/10 of a car? That doesn't really make sense, does it?
22.
So we'd have to round up to 22. 21 wouldn't be enough. 22 would have been enough. Then we would have broken even if we sold 22. Does that make sense? Yeah. Okay. So that's the point I wanted to make there, is that what this really means then is x would have to equal 22 cars. That's how many we'd have to make to break even, right? Everybody get that? Yep. Okay, good. All right. We will wrap this up tomorrow and you'll have some work time.